Hello, it's James from Small Form Factor Network, and today we're going to do another episode in the SFF Forum Designs an eGPU case. So this is episode 5. Last episode, episode before last, I had kind of experimented with some vent patterns, and then last episode I kind of ended up fleshing out this kind of cube, cube grid type of pattern, which I think it looks pretty decent, and it's definitely an open enough pattern that there shouldn't be any problems with airflow, but also it's manufacturable, because I think I forget who proposed it, and then Funks did like a mock-up of like one that was kind of a similar type of pattern, but using like small holes to kind of give you kind of a shading effect, which I really like how it looked, but it just wasn't manufacturable. So this one kind of ticks all the boxes. It's something that could be relatively easily cut on a laser, and it's got airflow, and it kind of looks more interesting than just like a bunch of like slots or something like that. And then this episode, I need to do some fine tuning on the vents to make fan holes for either maybe mounting a radiator for like a Fury X type of system, or at least if nothing else, just like dust filters. But I'm sure you people wouldn't want to watch me for 2 hours just fiddling around getting the spacing on a vent pattern correct, so we'll do something else. And then let's see, the InWin 303, I don't even know what that looks like. Let me just, whoops, InWin 303. Oh, you mean just like really big hexagons? Yeah, I mean that would work too. Other side? Yeah, you mean like this? Like the hexagon pattern? Or am I missing something? The other side. The back side? That's what I was... Oh, like this? Oh, that's not very good. Let's see if I can find a better picture of it. You wouldn't think this would be so difficult. It's kind of... Yeah. It's like nobody has a good picture of the back. Well, it's not a very open pattern, though. Man, I can't believe nobody has a better picture of it than that. Let's see here. InWin 303. Okay, let's try that one. Yeah, it's still like, I'm looking for like one that's just like a straight on shot of the backside, but just so we can get a really good view of it, but apparently it doesn't exist. But I mean, anyway, you can kind of tell here though, it's like, I mean, it looks interesting, but it's not a very open pattern, since the ventilation or the airflow just has to go through like the small vented area between the hexagons. So I don't know, it does look interesting, but yeah, it's not a particularly open pattern. So yeah, I mean this isn't set in stone. If somebody comes up with something better, I could look into it, but for now, I mean, I'm pretty happy with this vent pattern. So yeah, and let's see, I think what I'll do, but yeah, like I said, I don't want to, I mean, I guess I could, but spending two hours just filling with the vent pattern, getting the spacing lined up would be so boring. So I'll do that on off the stream and figure out something else to do for this. So I think one of the things I do want to do, yeah, because let's see, back cover, yeah. Because one of the things I do want to do is get the screws figured out for the other cover. Because one of the things we had done is, let me zoom in here a little bit, is so the flanges and stuff for the frame piece. So I think I have that kind of figured out where I want them. There's a little fine tuning that needs to be done, but it's kind of basically where I want it. But the problem is that to kind of get these flanges like this leaves all these kind of ugly relief cuts and stuff. So like kind of like these cuts and like stuff like this, just it looks ugly. And what it is like with the cover on. Whoops. Oh yeah, it just has the pictures that I was using reference. Okay. So like if you look at it from the front, then you see kind of like the bends and the relief cuts, and it just doesn't look very pretty. And though like the standoff holes here, it looks like really bad, but in reality it won't really be very noticeable because I'm assuming that this would all be powder coated. So the powder coating will kind of hide where the standoffs are pressed into the metal. I mean, it's not perfect. I mean, even textured powder coating, if you look at it at a right angle, or if you look at it at just the right angle under the right lighting, you can definitely see where the standoffs are, but it's not usually too bad. But the front here, there's not a whole lot we can do about that. So what I was thinking is we'd have just a separate L-shaped piece here to kind of match the cover. So it would look like, yeah, so it'd be basically this. It'd just be this kind of L-shaped piece of metal. So pretty straightforward. I keep doing that. But what it is, if that's gonna happen, we'll need to find a way to mount it. And one of the things I was thinking, we'll need at least, yeah, we'll definitely need 4 screws on the back, just kind of in the corners, kind of like the cover, about lined up with the covers, kind of like right there, there, and there, and there. And then the front, I mean, it won't look symmetric, I guess, but I mean, I think, yeah, like some inlay or something. I just wanted something basic, just so as a like a default, and then people can like come up with other solutions if they want. And in the front, I was thinking maybe, though I guess if you did have like a wood inlay or like some kind of like accent panel on the front cover, I guess you would want 4 screw holes so you could screw it in. That's an idea. Yeah, that is an interesting idea. So I think what I may do then, yeah, I think I'll go ahead and put 4 screw holes on the front. So then that way you could like cut out like a little rectangular accent panel and then just screw that to the front. Yeah, that's a cool idea. Let's do that. All right, let's open up the frame piece. So I'll need to put 4 threaded holes on the front then, so that you can screw your accent panel like wood or whatever, like wood, acrylic. Yeah, that'd really be most of it, I guess. Anything else would probably be too expensive to do. Let's see. So that'd be 4.22, and the 4.22 number comes from the hole size for the PEM nut is where that number came from. And then what I'll do, let me see, where else are there PEM nuts? Oh, there's one. So there's others in the frame. And then that should be the right size. So yeah, we'll just copy this. But yeah, if you ever like doing case design and you want to think about if you're going to use like PEM certs, like the dimensions you need for like the hole to mount it in is all going to be on the spec sheet. So, oh, whoops. Actually, no, I'll do an assembly constraint. So that way if I move that hole, then I don't have to worry about it. So do that. And then I'll do a tangent. Oops, cannot create assembly condition. Pick reference to align, pick geometry. Ah, come on, there we go. Okay, so I'll turn that back off. And then I guess I'll consider how much spacing I want. Because what it is if you do use wood, you wouldn't want the countersink, assuming if you do a countersink instead of just like a pan head screw. If you do a countersink, you don't want it too close to the edge. So I really don't know what rules of thumb are for like doing like a countersink in wood. So probably 10 millimeters seems too small. But it'd only be M3. Then again, you couldn't really have it that thick, I don't think. And then, let's see, it's at 15 now, which kind of looks weird already. So I'd say probably just 10. Which looks like a huge gap here on the model, but in reality, that's only 10 millimeters. That's not that much. So, and we'll say that's good. Top bend. Yeah, that's good. It'll keep it symmetric. So, yeah, we'll just do that. Let's say 10. And we'll make one to the bottom. 10. All right. And turn that back on, and it's constrained. Do a alignment constraint. No. That was weird. Okay. Let's see. Copy that. And then do align. Okay. So there's our PEM certs at the front. And then this is a, what is this? Oh. I need to fix that. I keep forgetting like the numbers don't line up nicely. Let's see. Where is that messed up? Oh, that's a weird number. 68.3. 68.3. Probably what I'll do, I think I'm constrained by this. Oh, great, something moved. What moved? Oh, I think I accidentally aligned the part to the, okay. I did the, yeah, I did one of the assembly constraints in reverse is what happened. Okay. Let me fix that. Nope. What did I do wrong? Because those are all part of that. Yeah, I think it's because I did not have the blind standoffs constrained. Oh, but I do have, okay, yeah, I see what happened. It's because I had all the nuts constrained but not the standoffs, and then I accidentally did one of the constraints backwards. So then it moved everything else in relationship. And I think I screwed something up. What did I do? Yeah, I messed something up. I guess it doesn't like it when I move those. Whatever, I'll just move these. Since they're not constrained. And then I'll just move this back over because I screwed up and I should have had everything constrained properly, but whatever. Let's see, I need the standoffs to the back of the PCB. Okay. Okay, now all's right. Okay, so what I was saying is let's see, I think this is flush with that. Yeah, I want to make it come out to a nice number so we don't have to have these weird like point whatevers and such, which is not fun. And this is not level. How'd that happen? Oh boy, I really screwed something up. There we go. Oh great, I think something's tilted. Yeah, I messed. Oh yeah, everything's at an, oh great, everything's at an angle. Control Z. It's one of those last PEMSerts I did. I did one of the relations backwards. Okay, let's try that again. Make sure this is all still lined up. And it is. So, all right, let's let's try that again. Do this, do that, move it 10 millimeters. Let's see, and let's see, that's there, that's there. Okay. Okay, we'll just be more careful in what we click on. So align this to this. Okay, that's that. And then make copies of both of these. Oops. And let's see, this one. Okay. And do an align from there to there. And then do an align from there to there. Okay. And I'll be lazy and not worry about tangent because I don't think that's going to move. Okay. Now let's check this again. So this to here is XYZ 68.3, which is not a nice number. And actually, let's see, what is this reliant on? Oh yeah, it's reliant on this. Okay, we want it to be basically flush. And that's 0.06. 0.06. And I guess what it is. Okay, I don't think this is perfectly, yeah, it's not perfectly aligned. So we have a little bit of wiggle room to move this back and forth, this piece here. So I think what I'll do is I'll go ahead and move it let me just move it out of the way. And let me see, it'll be easier if I open the frame. So I want it to come out to an even number is what I want it to do. So let me just, oops, let's see, I don't want to do that. It'll be, okay, yeah, good. Yeah, good thing we constrained them anyway, at least in this dimension. So if I select all of these, select that, and okay, yeah, all right. So I'm going to make this come out. Basically, I want this to come out to 68 instead of 68.3. There we go. Okay, so what that should do is now the spacing on these holes are still messed up. Why did it get messed up? Oh, yeah. It's because the holes didn't move with them. Okay. We shall get this right eventually. So we'll do 10. There we go. So now 48. Okay. So this is where having a parametric program would come in handy. So there's like a lot of times now where I wish I had done a parametric program, parametric modeler, because then it wouldn't have any of these issues. So, but now it's fine. So what would happen now is we have a 48 by, and this will probably be in, yep, 162.2. So I need to fix that too. So that comes out to a nice number, but that's pretty easy. I can just move the bottom part up. So that way you can just have like a, let me see, how do I want to do this? Let's move this back. Whoops. And put the cover back on, turn that back off. And let's see, make a new part. Let's say wood accent. Oops. I guess if we design it like this, we would want something more like this, I guess. And then, I don't know, let's say 2 millimeter. I think this would probably, yeah, I think this would work out easier or nicer. So yeah, maybe go ahead and just like not cover up the backside here. So you would have a little bit of a gap here where the relief cut is for the top, and so at the front edge and the back edge, the little relief cuts there, and then also there, and then there. But they'll be relatively minor, and plus they'll be on kind of like the back side. And then so on this front piece here, then yeah, you could do like maybe like a piece, like a thin piece of wood. So like, I don't know, whatever, birch or something like that. And then you could just put some countersinks in that pattern, and then you could attach it to the front. Yeah. So that would work. And then, oh yeah, Brian, how much will it cost? So, it's basically a really similar design to STX 160. Because let's see here. If we look, the frame is the most complicated piece, and it's about this relatively similar complexity. In some ways, it's more complicated. There's more standoffs, but in other ways, it's simpler. There's more metal because it's a little bit. Well, is it? It's a little bit bigger. Yeah, it is. More depth, less width. Cover is simpler. Well, I guess cover's about the same. I think STX 160 had more cutouts, but I think there was like less vented area, so I think the amount of like cutting length would be about even out. So it should be, and then I guess there'll be another piece for the front, but that'll be really simple. And I guess by default it'll be just like a piece of aluminum, but then you could like swap it out with like something like a piece of wood or some like acrylic or something as an accent. So yeah, it should be about the same price. So STX 160 is, I think it ended up being about $500 for 2 units. And like, so there's some extra cost involved. There's a setup fee, which I think is, ProtoCase has a $70 setup fee per order. And I think that's so to account for like, if you order like one really simple bracket, like it may only cost $5 for the bracket itself, but then like somebody has like set up the machine and process the order and stuff like that. So ProtoCase has a $70 setup per order. Just no matter what you order, if it's like $2 bracket or like $1,000 prototype case, then it's a $70 setup fee. So yeah, so I think it was 500 including that. So something like that. I forget all the math, all the numbers figured up. So anyway, basically around $200 to $300, I would think, depending on how many. So of course, as the price or as the order quantity goes up, the price per unit goes down. The ProtoCase, it only goes down so much since their pricing is oriented for prototype runs, like the name kind of says. So yeah, even if you ordered like 1,000 from them, it doesn't really make sense because they just don't have the equipment to really do that 1,000 units cost effectively. So you'd really be better off going to a different type of manufacturer for that. But for this project, I think probably the most that would ever be made would probably be like 10. So it's not a big deal. So let's see. So yeah, you can have some kind of accent panel. So yeah, let me get rid of this since we don't need it. And let me see. Let me open the frame back up. And I guess the side effect is that... okay, I'm not sure why that doesn't line up. But yeah, we'll need to make it so that this panel is flush with the frame again, since we're not going to have that other panel sticking out. Yep, there we go. And let's see, what else did I need to fix? Oh yeah, I'll go ahead and fix the height while I'm thinking of it. So that's 182.2. So let me see. I think we'll just move all of this up 0.2 since it's not really going to have any effect on the fitment of the HDplex, and then that will give us a nice even number. Not that it really matters, but whatever. And then if we go back to the cover, and I think, so different parts of this don't line up. Okay, may need to fix that. Yeah, let me fix that. For some reason these parts aren't, no, they're coincident there. Okay, they're not here though. Okay. So yeah, this is kind of like the downside of direct modeling, is that like you can run into weird stuff like this, or like it doesn't line up anymore for no apparent reason. And then you had to go and fix it one by one because there's not like a drawing or a sketch or something you can correct it. So, and this is the thing, is like there's not any one answer. I mean, because like direct modeling has its disadvantages for sure for stuff like this. So like if you mess something up, then you have to go in and fix it, usually in multiple places rather than just having like one dimension in like the original sketch or something like that you have to fix. But the advantage is that if you can have a mess of a model and it's not a big deal, because you can go and just dive into any single point of it and then make corrections instead of having to go through the whole feature tree. So yeah. And then I guess let me check if these are... They're not, but these should be coincident. Yes. Okay. So that's all fixed. Yeah. Okay. So that's fixed. And actually, there will need to be a gap between them, because here I just have it modeled so that they're flush with each other. But that doesn't really work in reality, because like when you're designing sheet metal parts, or actually just any metal parts in CAD, the CAD model should only be of the bare metal, or if it's got if there's a coating that's like part of the metal, like if it's galvanized, I think you can include that too. But like if it's a coating added in a later process, like paint, then actually you don't include it in the model. It's just the metal. So you had to account for that though. So actually, and I'll just have to do this later. I'll need to figure out what it needs to be. But yeah, there would need to be like a gap between these, because what will happen is after they're powder coated, the powder coating will add a little bit of thickness to it. So there needs to be enough room for the powder coating, because if we had it like this and then we powder coated it, then yeah, they'd be a little bit too tight. Which on this one, it's not a big deal, because like basically this is just a U piece, so you can kind of just flex it open a little bit more and it wouldn't be a big deal. But other types of sheet metal parts or metal parts where it's more tightly fitted together, then that could become a problem. Especially like, I guess if you have, I guess the most noticeable place you would run into a problem like that is if you have a hole in like especially if it's like a fairly deep hole, and then you have like a dowel or a shaft or something like that that's supposed to mate into it, then yeah, if you didn't account for that and they're like both exactly the right size in the metal, and then you paint both of them, then like the only way you're going to get that part in there is if you just take a hammer and just like scrape the paint off or something. So yeah, we'll see. Ryzen stock cooler, I don't even know what you're talking about. I haven't seen that. Is it not the Wraith cooler that they bragged so much about like a couple months ago or a year ago? Because there was that, they make it a big deal about the Wraith cooler and all that stuff. So I would assume that it's the same thing. I would hope so. And let's see here. Oops. 2. Oh, the 65 watt TDP thing. Yeah, we'll see about that. I'm a little skeptical. I mean, it is a little bit easier than Intel since they don't have integrated graphics, because a part of the problem with the Intels is that it has those integrated graphics that they have to account for. So they can only make it so the TDP so low, because the TDP has to account for what would happen if both the CPU and GPU are under load. So Ryzen doesn't have that problem since they don't have any, or at least the processors that will originally release will not have integrated graphics. So that helps, but we'll see. Oh, I wouldn't doubt it. Intel's stock coolers, as of the last several generations, are pretty pathetic. So yeah, I wouldn't be surprised at all if they're quite a bit beefier than the Intel ones. Let's see here, M3 close fit countersunk. Oops, did it backwards. Oops. Though I've been running X99 for several years, so like I just don't ever think about stock cooling anymore because they don't have any. Okay. Yeah, alright. So yeah, you could have you could do like this piece of wood, like in wood. So you just cut a rectangle, round it off the corners, put 4 countersinks in it, and bam, you're done. You can have your little accent on the front. And you don't even have to countersink it really. So that'd only be if you want flathead screws. But I mean, you could just drill a hole and just use it like a panhead screw instead, or a socket cap or something like that. But I imagine the default would be aluminum, since I don't think Protocase would be able to do that in wood. So, and then let me see, what's the thickness? 1.6. So yeah, actually this would be aluminum. So it's green, but that's just the default color. So it would actually be aluminum for the default. But then you could swap it out with a something else, get a different color. I think it looks good. Let's see. This is 11.8. is 12. So, okay, so that's why. This needs to come out a little bit. Or wait. Okay, so I guess here's a thing to keep in mind, because there's two ways we could go about this. So the problem is that if there is a front panel on the front, that means there's more material here at the front than there is equivalent at the back, because the back there's just the end of the frame and that's it. So the screws here, we have two choices. We could either offset the external screws symmetrically. So like this would be the same distance here and this would be the same distance here. But the problem is because on the frame it's not the same distance, we would have to offset the threads that those match up to, which we could do. But then, and the advantage is that means that this panel can be mounted either way. So you could either have it like this, or you could like rotate it and it would still fit. Which if the vents are symmetric, then that's fine. Or like if the panel is otherwise symmetric, then it's actually better. Because like with parts, it's not usually a good idea to have stuff that's almost symmetric, because it makes it a lot harder during assembly and manufacturing. In this particular case, it's not going to be too big a deal because it's a fairly straightforward part. But like, it would be very, very bad design to have something where like a critical component has like a bunch of like whatever, like it could be like a flange or a hole or a nut or a mounting stud or a cutout or anything. Just if it has a bunch of features that are almost symmetric, that's a horrible idea, because then during both manufacturing and assembly, either at the factory or the end user has to pay extra close attention to whether it's in the correct orientation. And if it only is very slightly off symmetric and it's hard to tell which orientation is which, that's bad design. So generally, you either want it to be symmetric or you want it to be very not symmetric. So it's very obvious like which orientation the part should be. In this particular case, I think what I'll do, because I think the vent pattern will end up being mostly symmetric, so it's not going to matter too much. No, that's what I'm saying. There's going to be more ventilation. Because the vent pattern will come down further and then it'll extend forward further. So this is just temporary. I need to redo the pattern. I need to fix it so that the spacing is better aligned to like 120 millimeter fan holes. So yeah, the pattern here will be changed to better line up. So it'll be mostly symmetric. So it wouldn't look bad either way. And really, it's not going to be, I don't think it'll be perfectly symmetric because the fan holes will be slightly off. But that would only be necessary if you're one of those crazy people who wants to put like a Fury X in here. For everybody else, it's not really going to matter. So I think we will make it externally symmetric. And then, yeah, we'll do that. So part of it, what I'll need to do is that I think there's enough material there. Let me see, because this is 6 millimeters. I think 4.8 is the minimum center line to edge. So that's 1.1 more. But I think this one to be lined up needs to be 1.6. That's cutting it a little close. So I think what I'll do is I will make this more like 14, and then we will do the same on here so it looks symmetric. Yeah, you'll be pretty limited on what cards you can put in here. It's just kind of I mean, the problem is if you make it big enough to support everything, then you're just right back at like the Razor Core or the Power Color Devil or whatever it's called. So it's just kind of pointless. Let's see. And then what I want to do is the frame, turn that off. Just turn the solid on. And then if I did everything correctly, coincident. Yep. Though, I mean, it's not really I mean, especially this generation, there's been so many small cards announced. Because I think last generation is if you wanted a 970 and you wanted it short, I think you had the Gigabyte and the Asus, and I think that was it. That was really your only choices. Whereas this generation, if you want a 1070 that's short, you have, let's see, Gigabyte. Let me see who. Gigabyte, Zotac, Galax. MSI is teasing a short card, which I'm assuming we talked about this in the podcast this morning. I'm assuming that's going to be a 1070. So it's looking very much like. Oh, that's not lined up for some reason. No, this should be moved over. That's why. It's very much looking like MSI will release most likely a 1070, possibly a 1080, though I don't think that's very likely. And why is this not lined up? Oh, that's weird. So yeah, there's lots of short cards this generation. So I don't think only supporting short cards is really that much of a limitation compared to previous generations. There we go. Okay, now it's lined up. Make sure it's lined up that way. 8mm. That's good. Zero. And then why is this not lined up? 0. Something's weird. Oh, it just looks like it, because of the curve here, it looks like it extends a lot further than it does, but it doesn't. Okay. Yeah, I think that'll look pretty nice. So, yeah, like I said, you'll have these like kind of this little ugly gap here on the back panel, but other than that, I think it'll look pretty nice. Because I mean, I guess it's kind of like your normal tower. Like a lot of cases are designed where like they're kind of assuming that like the window is on the left side of the case because they're assuming it'll be to the right of your desk. And I guess we'll just kind of do the same thing here. So like if assuming the dock is on the right side of your desk, it'll look pretty nice. And then otherwise, and it won't look quite as pretty, but whatever. And then if you have it kind of sitting horizontally, then this would be the bottom, and you just put like rubber feet on it or something. So yeah, MSI is teasing. Let me see if I can find it. Where did I see that? MSI short card Facebook. They were teasing it on Facebook. Let's see, past week. I don't know where the link is. Oh, is that it? Yeah, here it is. Whoops. Let me copy. Yeah, it's this. Nah, go away, Facebook. So obviously, and because what it is like, it can't be a 1060 because they already have a short 1060. So like, why would they like hype up like another short 1060? It wouldn't make sense. So it really would only make sense if this is a 1070 or 1080 for them to hype it. And actually, I guess it could be a Radeon. I hadn't thought of that. But I kind of suspect it's an NVIDIA. So yeah, my bet's on a 1070, but I think there's a couple people saying that the card in the background I think is their 1080. MSI GTX 1080. But I don't know. I don't see, because that would be a really, really short 1080. Because even Zotac didn't go that short because of the heatsink. Let's see. Graphics cards. I bet you guys can't guess what MSI's favorite color is. Let me see. Okay, no, they do make a 1070 with that cooler. So they do make a 1080 with it, but then they make a 1070. So yeah, so here's the card in the background. So, I mean, they have a 1070 of that cooler design and the 1080, but yeah, I don't think they would have done it. But I would love to be pleasantly surprised if that was actually a 1080, because that would be a tiny 1080. That'd be even shorter than the Zotac 1080. So that'd be cool. We'll see. But yeah, that would be amazing. Okay, so we got this here. I think I have most of the screw holes fixed as far as the exterior. Because let's see, we got the 4 for the frame, and then the 4 for the front, and then oh yeah, the let me do this. Nope, no. There we go. Okay, so one thing is that let me see, how did this work? Let me see. Let me pull up my pictures if I can find them. Projects. Nope. Just a second. There it is. Nope. Somehow I misplaced them. How did I do that? Well, I guess somehow I misplaced all the pictures I had of the Ikitio. Anyway, so this part here, which is part of the Ikitio, is, let me think, it's threaded, if I recall, because, yeah, it'd have to be. Let me see if I can find the pictures, though. Oh, there they are. Okay, let's see here. Okay, yeah. Yeah, so yeah, that's right. So yeah, these holes here and then this hole here are threaded. Yeah. Because we'll need to have holes in the frame for those. So let me see, that ends up being about here, and let's see, we probably want to just go ahead and do countersinks. M3 close fit countersink, and it won't let me because it's too shallow. And we'll just cheat. Let's see. How do I want to do this? Oh, I know. Suspend. There we go. Insert. Yeah, because it refuses to make countersinks that are too shallow. So I just sometimes have to kind of work around it. Okay. So now if we go back here, turn the frame back on, turn the cover off, and we'll just line that up approximately. I'll need to kind of dial this in later, but I just want to kind of make sure that it'll work as it is. It's like one thing I'm already seeing is that may be too close to the edge, like this countersink here. Because a lot of like best practices or like guidelines and stuff say to have countersinks, I think 8 times the material thickness from the edge, which I think is just way too conservative. Because like 1.6 millimeter aluminum, that would be like what, 12 millimeters or something like that. So I think what we'll do, it's on the rear, so it's not going to be really that big a deal. So I think we'll go ahead and assume these will not be countersunk. Let's see, activate. Because yeah, it is a little too close to the edge. So these will just be normal screws. Okay. There we go. Okay. So there's that. So what it is like in the model, I just have this as just an empty hole because I was just being lazy. But the actual part has like a threaded insert right there. So that's what that's going to do. So yeah, the screw will come in through here and it'll attach to this piece. And what it is, I guess, just so we're clear, this is a piece that comes with the Akitio dock, and it's where the GPU attaches. So rather than like making our own thing, is we might as well just reuse this since we'll have that part available, since we need the Akitio for its PCB anyway. So yeah, we'll just make good use of it since it's already there. So that takes care of our video card. And then the only other part is like, so there's the slots to kind of retain the bottom edges of the video card's retention bracket. And then this is also a threaded hole right here. But as you can see, it's a bit of a problem since it's just kind of floating in the air. So I'm not really sure how to handle that. So a couple ways we could do this. So one way, how would I do that? I was thinking maybe extending this and having a standoff, but that's a threaded hole. So that would be, yeah, that would be rather difficult. Oh, I know what I was thinking of to fix this. Yeah. So there's a hole right here, and I guess I forgot to model that in the part. So there's a hole here, and this is for, what is this for? Oh, I know. It's, let me pull it up. So there's a hole here and a hole here, and what it is for these. Let me see if I'm recalling this right. I believe, okay, it's indirectly for these, because what happens is, I think this picture shows it. Yeah. So what it is like, it's a little hard to tell what starts where, but, oh yeah, that's a good idea. So let me see, brush tool. Okay, make it a little bigger. Okay. So what happens is that So this part, like this part right here, is basically like this. Is this piece here. Oops, I can't draw. And so the rest of this is the frame for the eGPU. And so what it is there's this threaded nut here on the frame piece, which is for these screws here. And so there's a hole here in the bracket. Yeah, like this hole and then this hole. And they're for this nut to kind of fit inside of. So that's what they're there for. But I was thinking we could reuse them. So what it is like, let me add it here, just kind of a rough placeholder. Let me see. Just put it there, and I'll just purposely put it in a wrong place so I know to fix it later. So there's this hole here, and it looks stupid because I did that on purpose. So I know, like, I'll know later, like, hey, that looks stupid. So then I'll remember to fix it. So I was thinking maybe putting a hole on the frame, and then so you could put a screw through it, and then have like maybe like a little nut and maybe a washer, and then that would kind of hold that in place. That's what, yeah, I remember that. Yeah, so just, yeah, because I think it's small enough in reality that you could put like just a small washer on it, to kind of hold it, and yeah, and then that would kind of just keep the bottom edge of the bracket from kind of like moving back and like forward towards the front of the case, away from the frame. I mean, it wouldn't be a huge deal if it's not really secured, because like once you have the video card installed, like the tabs of the video card will kind of catch these slots, and that will kind of hold it in place. And then the video card itself will be held in place by the PCI Express slot on the circuit board, which of course is held in with like several standoffs. So not a big deal if we don't really do anything about the bottom of this. I was just thinking if it wasn't a big deal, it'd be nice to kind of secure it just for completeness. But yeah, it wouldn't be the end of the world if we didn't. So and yeah, it's really tiny, so it's not like there's anywhere for all these parts to go anyway, because like it's just all going to be crammed in there. Because the only other thing, because like this hole is actually threaded, so I was thinking like some kind of standoff solution, but I think that would be more effort than it's worth, because the only other alternative for that would be another bracket. So like a little bracket that's attached to the rear here that comes up, and then that's the thing with sheet metal. And I guess this is kind of true of manufacturing in general, is that the more parts, the more expensive. Because some people talk about how like having like one like washer or grommet or something is like a trivial expense. But the thing is like it may not be very much of expense, but it is an expense. It doesn't literally cost nothing. So like every little part and detail adds more cost, which we're not mass producing these things, so it's not a huge deal if it adds like $2 or whatever. But it is like the less parts, the less expensive. So generally that's how you want to optimize sheet metal. Because you can optimize it all you want, but at the end of the day, it's just more parts is more money. So, so yeah, I think, I don't know. I'll think about, because the thing with that is that it's a little messy if you have like a nut and a washer, because that's just kind of like a little fiddly assembly, which is always no fun. So I don't know, I'll think about it. But I think we won't have too much of a problem just not having it, not relying on it. All right, what else? So I think we have all the attachments accounted for then, because we have the standoffs accounted for. We have all the screws and countersinks for the exterior panels. We have now added at least the bare minimum screws for this little bracket here. So I think we're pretty close. The only thing we're really missing, other than, like I said, I need to finalize the vent pattern, is the hole for the Thunderbolt connector, which I need to measure the Akitio board and figure out exactly where it is, so I know where to put it. So I need to do that, but I don't actually have the Akitio on me, so I can't just measure it right now. Let's see, what else? I think we've about accounted for everything that I can think of. Because I think on the exterior, we're pretty much done, other than the vent. And the interior, I think we're pretty much done, except for some of the details. Like I need to round off corners here and there, of course. Can't forget that. And then the hole for the Thunderbolt connector. And what else? Yeah, I can't think of anything else. So I think that's mainly it. Let's see. Yeah, I think that'll work. So, but yeah, like I said, it would be extremely boring to actually like finalize the vent pattern here. So I'll just do that later. So I don't know. You guys have any questions or anything you want me to go over? And it doesn't have to be with the eGPU case. I could cover something else. Oh wow. Okay, let's rephrase this. Any questions related to like SFF or sheet metal design or CAD or anything? But yeah, no politics. Let's not get into that. The Enermax case. So yeah, let me pull that up real quick, actually. Because I do have a couple beefs with it. Let me see where to go. There it is. So the thing is that it's micro ATX, but it doesn't really support micro ATX fully. Well, it does, but let me see. Where's the picture? Come on. Ah, here we go. So, because when I first saw pictures of this case, I was assuming that the bottom and maybe or let's see, what was I thinking? Because the way it looks externally is it looks like there's a lot of venting. But really, once you actually get into it, the bottom is solid, the top is solid, the front's only partially vented, and even then, you can't even really use the whole front of the vent. Like it's only limited to a 120 millimeter. So, and then like the side of it's glass, so there's no venting there. So like the ventilation on this thing, frankly, is just really bad. On this Enermax steel wing. So like if I was designing it, like what I would do is like I would have it so there's this kind of like there's this curve here and then it comes straight down, but then there's like this exterior panel here. So I would have the internal frame, I would just come down at a straight angle, and then I would have all of that vented and with fan mounts. So then that way you could fit, you may have to like deepen the case a little bit so it doesn't hit the motherboard, but then you could fit like a 240 millimeter radiator instead of just a 120. And then I probably would have vented the rear and put a little bit taller feet on it to give you additional like ventilation options along the bottom of the case. Power supply where it is okay. It's not great because it is covering up the motherboard. So yeah, I mean, it looks nice, and the aesthetics are interesting, especially like kind of from the front with kind of those just, I don't know, it looks neat, it's interesting, but oh yeah, it's only 3 slots, so it's not even full micro ATX really. So yeah, I mean, it looks cool, the build quality looks good, but the internal layout and like the internal design, especially for cooling, is not what I would have done. I would have done it much differently. But yeah. So 2mm inner radius for 2mm steel. So yes, basically on steel, I mean, it'll depend on what type of steel. So like tool steel is, well, you can't really do sheet metal with tool steel, but like your normal sheet metal steel, you can generally do a 1x material thickness for the bend radius. So if it's 1mm thick steel, you could do a 1mm bend radius, and then if it's 2mm steel, then you could do a 2mm radius. Though so the thing is with bend radius is if you're modeling it, let's see, this is a sheet metal part, and we'll pull it. We'll say that it's 2mm. Okay, so I think Space Claim, for instance, defaults to 1x. Yeah, 1x the thickness ratio for the bend radius. So this is a 2mm steel, so it has a 2mm inner radius. So the thing is that I wouldn't get too caught up on that. Just know what it is generally, because the thing is that what exactly the bend radius will be is mostly dependent on what tooling the manufacturer has. Because let's see, where do I show this? Let's see, I don't know if I can find a good picture to show this. Yeah. So here it is. Here it is. So like, so the tooling, like the different like pieces that go into the press brake in order to actually do the bends. So that's this kind of gray piece here in this picture, or bluish gray. So like the radius of that tooling, of the tip of that tooling, that's going to be a big determinator of the bend radius once it's actually manufactured. So it's not going to be like, you don't know exactly what it is until you decide on a manufacturer and you know what their tooling is. And even then, it's going to vary slightly depending on just like what, like I said, what type of steel it is, what type of bend it is. So I would not get real caught up in dialing in the bend radius exactly right in the CAD model, because it's not going to matter as long as it's close. So that way you can make any decisions that are particularly reliant on it. Like if you have like cutouts or stuff that had to be, that can only, like if you have like say like a PEM nut that can only be so close to a bend, then you would want the bend modeled for sure. Like you wouldn't want to just have like a perfect 90-degree angle, because you would need to account for how close the PEMSER is to the bend. But as long as it's close, it's good enough. Because the manufacturer, when you send them the CAD model, they're going to run it through their CAM software and then convert it for like to actually figure out what exactly it'll be after it goes through all their equipment. So as long as it's close, it's good enough. I wouldn't worry too much about getting it exactly right. And it'll depend on the material. Generally, aluminum, you can't bend it as tight as steel because it's softer. So it's, or let me see. Yeah, it's more likely to crack is the problem with aluminum. So you can't bend it super tight. But yeah, just get it close. It doesn't have to be perfect. And then if you, I mean, of course, this is kind of like, if you don't know what manufacturer you're going to use, you can't really ask them. But if you have enough manufacturer in mind, then you can just ask them like what bend radius they recommend. So you can kind of have it somewhat closely modeled in the CAD. MXM. Really, the problem with the MXM is availability. So like people could come out with the awesomest boards, but if you can't buy an MXM card, then it just kills it. So AceRock has said that they're going to address the MXM card availability issue. Like like with the Desk Mini RX and the Desk Mini GTX, that they will come with the MXM card. So obviously that fixes the availability issue because it just comes with it. The issue then is going to be like upgradability. Like let's say like the NVIDIA, I don't think they'll call them 1100 series. I'm assuming they're going to do a renaming scheme again. So whatever they end up being called, 1100 or 2000, or if they just completely reboot the naming with something entirely different. So like once those come out, the question is going to be, will AceRock make standalone MXM cards available for customers who have previously bought their micro STX systems, the bare bones or just the motherboards themselves? That's really the question. So if they prove that they're willing to make those cards available by themselves at a reasonable price for people to upgrade these MXM boards, then yeah, I think MXM boards can become a thing. So micro STX or even like other form factors. But that's kind of the kicker, is if they don't do that and like you just can't buy an MXM card at a reasonable price to upgrade it, then it's just going to kill the form factor. And then basically it'll just be kind of back to square one, where like if you want to upgrade the video card, you basically had to buy the whole system because it's too expensive to buy the card by itself. So yeah. Yeah, the EnterMax would be good with a mini DTX because then you could use a thicker radiator. As it is with micro ATX though, it's kind of limited. So ATX, yeah, I think we had a discussion on the forum, I forget where, about a smaller, something smaller than micro ATX. It was, is it MicroFit? I think it's what it's called. Yeah, MicroFit 3. So what it is that I believe MiniFit Junior, I forget what the pitch is. Let me see. Pitch. Where is it? Oh, come on. Well, whatever it is. I think it's 4.5 or something like that millimeter pitch. And pitch refers to the spacing between the terminals. So like MiniFit Junior, I think is 4.5. I forget. Go away. Let me double check just so I know what I'm talking about. MiniFit Junior, and you see pitch referred to a lot in connectors, because it refers to the spacing. For example, like what they call the DuPont connectors, which is those kind of small, like just kind of flat rectangular connectors used for like your front panel headers. Those are a 2.54 millimeter pitch. So that's the spacing between the terminals. And then MiniFit is 4.2 millimeter, and then MicroFit is 3. So the terminals are like 1.2 millimeters closer together. So not a huge difference, but it is smaller. And you can imagine though, over like a 24 pin connector, I mean, saving 1.2 millimeters per connector adds up. So I'm thinking maybe this, and these are actually used. I think some HP slimline computers use MicroFit. So it's kind of annoying though, because like the power supplies they come with are custom, that have that custom 24 pin. So then if you try to replace it, because it's TFX otherwise, I believe. So then you try to replace it and then oops, the 24 pin doesn't fit. So these are smaller connectors. And then I think John did a rant recently about standardizing on 12 volt. So either 12 volts or even better, like 48 volt would allow fewer connectors. So you could have like theoretically a 6 or 8 pin connector for instead of the 24 pin, and then it would just carry pure 12 volt, and then maybe 1 or 2 extra wires for like power on and stuff like that. And 5 volt standby, I guess. And then that would just reduce. So you'd reduce the 24 pin to an 8 pin, and then if we do MicroFit, then you'd make, not only would it be an 8 pin instead of a 24 pin, it'd be smaller than the normal 8 pin. So it would dramatically reduce the size of the power connector for the motherboard. So I would love to see that. And then if we did 48 volt on top of that, then you could probably get away with like a 6-pin connector, because you would need less amperage because it's higher voltage. So I'd love to see that. So pricing, I don't know. The main thing is that really the pitch shouldn't really affect the pricing, because it's just a smaller connector, but it's just a smaller connector. It's not any other big difference. It's not fundamentally different. It's just a smaller version of MiniFit Junior. The main thing though is it's just not as common. So like pretty much everything PC related uses MiniFit Junior, so they're produced in massive quantities. So of course it's just cheaper, just because everything uses it. It's very available. So, but I don't think it'd be a dramatic price difference. It's mostly just a matter of getting the standard moved, which I don't know if that will ever happen, because it would basically render everything incompatible. Like if all we did was just go from MiniFit to microfit, it wouldn't be a huge deal, I guess, because you could just get an adapter. But then if we do like 24 pin for the standard motherboard connector to like 8-pin pure 12 volt, then that would almost render all current power supplies incompatible. I mean, you could do an adapter off the 24 pin, but that kind of defeats the purpose. Plus, it may not deliver enough 12 volt, since the motherboard would be using pure 12 volt and be doing onboard DC-DC conversion for the 5 and 3.3. And then if we did the 48 volt, then yeah, definitely nothing would be compatible. It'd basically almost be starting over. And then like at that point, it's like, why even stick to ATX? Maybe do like STX or something like that and just have all new cases as well. But I mean, it's nice to think about, I guess, but it's kind of like one of those things that would be such a huge shakeup to the PC industry that there's a pretty good chance it would just destroy the PC industry as we know it. Because we kind of take it for granted, but it's actually kind of unusual that the PC industry is like it is, where everything's for the most part interchangeable. Because I mean, you look at most any other industry, there's all sorts of like proprietary stuff, and there's vendor lock-in. I'm not really sure what even be a close example. I guess maybe cars. Like you can take an engine out of one car and put it in another, but I mean it's usually not trivial at all. It's like a lot of work, and then stuff will never really work quite right because it just wasn't designed for that vehicle. So there may be like a couple sensors that you just can't really ever hook up correctly, and you just may get warnings in like your OBD2 or something like that. Whereas if you look at computers, though, there are definitely issues, but it's kind of crazy to think that like you out of like thousands and thousands of choices for motherboard, video card, power supply, case, CPU, storage, like thousands and thousands of tens of thousands of choices for each of those components, making for like trillions of possible combinations. And it works for the most part. There's definitely stuff that doesn't. Like it would be very impressive if you fit an ATX motherboard in an ITX case, mini ITX case. But other than like obvious physical constraints, like space constraints like that, it's actually really, really amazing that all these things are interchangeable with each other. So, I mean, it's fun to think about, like completely redoing the standard, but then it's like I don't know, it's kind of a risk. Yeah, so I don't know, it's fun to think about though, just like what if we just had complete control over the standard, how much space we could save. Yeah. But I don't know, any other questions or anything you want me to talk about? Designing for noise. Yes. Yeah, because there's basically two approaches for that. Well, yeah, I guess there's kind of two approaches. So, like, the most common approach, let me see, like for full size cases, is kind of like Fractal is really well known for doing it now, but I think Antec kind of started it with the the Performance 1 series, like the P180 and such. So this is kind of like, well, let me see if I can find a good picture. So one approach is basically like so like kind of minimizing the exposure of the fans to the outside. So like kind of baffling and then sound dampening and stuff like that. So not as many good pictures showing this as I would want. So like what Fractal does is like they include various vent covers. So there's a cover for the vent on the side. I don't know about the R4, but some of the other models have vents for the covers on the top, and then the front fans are baffled, so you're not directly exposed to the fan. So the fans are mounted to the inside of the case here, and then you have this front panel which has a gap here for air to come in for the fan, and then you got kind of a little bit of a grill there, so it's kind of an indirect path for the fan. So that means that it's an indirect path for the noise from the fan. So that kind of helps dampen the noise. So that's one approach. So it's just kind of reducing the pathway between you and the fan. And I mean, they do put sound dampening. Realistically, though, the thickness of the sound dampening that they're using is somewhat useless. It's really not that effective. Like the amount of noise reduction you get from them, including the sound dampening, would be the equivalent of just reducing the fan RPM by like 100 or 200 RPM. Like, it's 200 is probably optimistic. So, I mean, it's not nothing, but it's vastly overstated. I see people all the time saying, "Oh, I'm going to make this case like so much quieter by just throwing on tons of sound dampening." It's like, unless the sound dampening you're adding on is like 10 millimeters thick at least, it's not going to be that effective. So that's one approach. The other approach, and I guess the problem with this approach is that by design, it mostly is only effective on larger cases, or at least like implementing it makes the case larger. So like having like the front fans baffled like this. I mean, you increase the depth of the case by doing this by at least 25, 30 millimeters or more. So that's one approach. The other approach would be, I guess, more like the N-Case M1. And I guess like the Dan A4 also, is that it's so small, there's not room to do that, to baffle it or to cover it in sound dampening foam or anything like that. So it takes a approach where like direct exposure to fresh air for the crucial components. And where's a picture of the inside? Oh, come on. Well, something like this. So like, I believe this is the C14 heatsink or the C12 Noctua. And what happens in the N-Case M1 is not so much with the C12, but definitely with the C14, is that it basically ends up right up against the fan mounted to the side panel bracket, or the side bracket. So there's like no wasted space. So like air comes in through the vent, the fan's right there, it goes through the fan, and then the heat sink's right there, and it goes through the heat sink. And then like the top is vented, so then the exhaust air just goes out the top, and then you could put a fan on the rear and goes out the rear. And then same thing with the video card to a degree, is the video card's there, and then like the vent's right there on the bottom close by. So like you can make this low noise by spinning the fans at lower RPMs. So like the fan here on the side, and let's see, it's on the left side of the case. So if the case is to your right, you're basically like, the fan is like directly pointed at you basically through the vent pattern. So like whatever noise that fan makes, you're basically directly exposed to it. But what you can do is, because everything, like there's no wasted space and the CPU heatsink has direct intake, is that you can run the fan at a fairly low RPM and still get good cooling, because it's not having to like suck air in through vents far away. Like the vents like literally like right there. And this is what I did on my M1 is I had the Noxious C12 because I don't think the C14 was out when I bought it or something like that. I think the C12 was all that was available. And I put a Noxua 140, or I think I had the 150. So it's like almost the size of a 140, but it's got like 120 millimeter fan mounts, so I could still attach it to the heatsink because it only had 120 millimeter fan mount clips. And I ran the fan at idle, I think at like 400 or 500 RPM. So even though the fan's like right there, because it's running so slow, it ended up being very quiet. And same thing with the video card is that I think at one point I had a R7260X, I believe, because I started with the 5750, and I think at one point I had the 260X, and then I took the stock fan and shroud off of it, and then I put a 120 millimeter fan, an actual 120 millimeter fan beneath it, mounted to the vent on the bottom. So then same thing is like there's like the intake vent, and then the fan's right there, and then the heatsink's right there. So the fan didn't have to work that hard to kind of pull air in through where it needed to be because the vent's right there. So that's kind of the other approach, is just like, just kind of have the venting well thought out and right next to where it needs to be. So then that way you can run the fan at lower RPMs. So even though like the case is fairly heavily vented, so like lots of holes everywhere for sound to escape, is like the idea is that the cooling is good enough that you don't have to run the fans very hard for it to stay cool, and so thus it stays quieter, even though like there's not really any sound isolation. So there's that. That's kind of the two main approaches, and then there's lots of details. So like there's water cooling, there's like my personal favorite, which is not caring so much about temperatures, because I think a lot of people are just way too cautious about temperatures, and like they run their systems much cooler than is really necessary, and so thus it runs louder than is really necessary. So yeah, that's one approach, and that's kind of the approach I take, is that, because I mean the processor is designed, ambient. I mean there's always everybody is always talking, my system basically runs at ambient. It's like as close to ambient as I can get it, which, I mean, there's different ways of looking at that. So there's, I guess if you're heavily overclocking, it can be useful, like keeping the temperatures as low as you can, because like, yes, I mean, it's not like, if you're running it at lower temperatures, then so to a degree you can run at lower voltages. And so then, maybe you can get a higher overclock than you could otherwise that's stable. But I mean, SFF, like real SFF, like stuff that's like truly small, because like if you talk like just ITX, like isn't really encompassing it, or it's too encompassing, I should say. Because that would include stuff like the BitPhoenix Prodigy, where you could easily do like a very heavily overclocked system because there's room for it. NKSM1 you could overclock, but then you start getting down to stuff like the Dan A4. Like for the most part, if you want anything relatively quiet, then you're basically not going to be overclocking the CPU on the Dan A4 because you're just so limited in the CPU heatsink. So something like that, if you're running at stock, then, I mean, unless you're just like really, really on the edge of power, so like your power supply is barely enough, which I don't recommend that anyway, then if the CPU is running at a slightly higher voltage, then it's not really that big a deal. So if the CPU is running on the hot side of things, like honestly, like personally, I have absolutely no problem if the CPU runs at like 60, 70, even 80 degrees under load. Like, I mean, some people would just like recoil in horror at the idea of their CPU running at 80 degrees under load, like constantly. But it's like, to me, like Intel, like once you really start looking at Intel's documentation, it's absolutely insane. Like they write pages and pages and pages of documentation, and it's not just like fluff, like marketing fluff. It's like really hardcore engineering technical stuff. Like especially like the server process, like the anything with servers really, like the design guides and stuff like that just go into just insane amounts of detail. Like if we look at the Intel Xeon Thermal Design Guide 2011, V1, V4, for instance. So here is the Xeon E5 V4. So this would be Broadwell E family. So this would be socket 2011-3. So we have, what is it? 40, little over 40 pages of documentation about this. And this is for the thermal mechanical specification and design guide. So this is the, basically this is everything you would probably ever want to know about designing a thermal solution for the Xeon E5 V4 processors. And so like they tell you just basically everything you could possibly want to know. So like the thermal profile here, I mean, you can see they got charts and graphs and equations and stuff, like an explanation of turbo boost and how it relates to thermal output. Like a breakdown of like what of all the components involved in the mechanical system. So like the heat sink, the thermal interface material, your thermal paste, the processor, and they kind of go into an explanation of like the IHS and then the die, and then like that red line is like the in this case it would be solder because they use solder on these chips, which they don't on like the consumer processors, and some people think that's them being cheap, but it's actually because the processor die on the consumer processors is too small for solder. It would damage the die if they tried to solder them on. So anyway, so on the red you got solder, then the die, and then the PCB, and then the socket. So like they go into this explanation of all the components involved, and then they tell you like you can see like some of the lettering here. So TLA, so that's ambient, it's kind of like above the processor, and then T case is like the temperature of the processor itself at the IHS, and then like you have here's how they recommend, like, because like, so like if you were designing like a thermal solution and you want to see like what the actual temperature is and not relying on the motherboard sensors, which may be wrong, is that the way they recommend doing that is that or is, I think this may be for the built-in sensor, I don't know, but like they're explaining like how exactly to, or like the exact specifications of how they measure the temperature for all this like documentation. Like it's incredible how much documentation and testing that they do. So the thing is, they don't just kind of wing it. I mean, they do lots and lots of testing and validation and certification, and then documenting all that stuff. So what it is like when they say that the processor's max temperature is like 100 degrees or 95 degrees or whatever, like they're not just like pulling that number out of the air. Like they've done like thousands of hours of testing to validate that that is a safe temperature to run up to. And so like to me, like if my processor is running under what they say is the max, then to me it's perfectly fine. Like some people may scream at the idea of just running their CPU at 80 degrees, but to me it's like it's designed to do that. If it's under the maximum that Intel has specified, then really I don't care. So and what that does is if you kind of let go of this idea that you just absolutely have to run the lowest temperatures possible, then that really frees you up to achieve lower noise. Because you can run your fan at lower RPM, you can get away with smaller heat sinks if you're trying to downsize it, stuff like that. So it's really freeing if you just want low noise. Because the problem is having low noise and small and quiet, or like, quiet and small and cool and affordable it's really difficult to do. Like, you can do the 3, and even then, like, at some point, it doesn't really matter how much money you throw at it. It becomes difficult to have, like, quiet and cool and small and powerful. Because if it's like an Atom processor, then yeah, it's pretty easy to make it quiet and cool, because there's just like, it's an Atom processor. It's like a 20-watt chip. MacBooks, yeah, they run hot, but MacBooks run hot because Apple has never learned how to properly apply thermal paste. Maybe they're better on the newer ones. I haven't taken apart anything relatively new, like within the last couple of years. But like, I think I've taken apart stuff as old as 2006 up till 2012. So there's at least a 6-year period where like they put way too much thermal paste on them. And it just causes them to run super hot. Yeah. So this is how much, oh, here we go. This is how much thermal paste that Apple recommended putting on for manufacturing. This is like their, I think this is their service guide. So like for like Apple technicians, if they're working on a MacBook, like here's what they say how much thermal paste to put on there. So yeah, like MacBooks run hot, but it's not so much because they're designed to do that. It's more because they just don't know how to put thermal paste on there properly. Because there's been many MacBooks where like it idles at like 60 degrees and then loads at like 90. And then like I take it apart, scrape off like the completely excess amount of thermal paste they put on there, clean it up, put the proper amount of thermal paste on there, and now it idles at like 40 and then loads at like 60 or 70. But so yeah, as far as MacBooks go, this is the problem. Cause yeah, this is actually what they recommended for a while. But yeah, I mean, laptops though, yeah, definitely laptops you'd see where, because it's like designed and spec'd by the OEMs, is like they're much less oriented on maintaining super low temperatures like enthusiasts are with their desktops. So like laptops, it's not too uncommon to see temps of like 70, 80, even 90 degrees if it's like a high-end processor and like a really thin laptop. So, and I think people could stand to kind of like learn from that for desktops. It's like you really don't. Yeah, exactly. Those laptops don't like the CPUs don't fry in a year. I mean, they last. I mean, even like MacBooks that are like running like that have way too much thermal paste like this and are running way too hot. I mean, you see them running like 6, 8, 10 years later. So I mean, they run way too hot, which makes the fan loud, which is annoying. But I mean, it doesn't cause them to like fail immediately. So like the longevity thing, I think is overblown as well. Like, I mean, to a point. I mean, if you're running at like 95 degrees Celsius, like just right under TJ Max for like 24/7, then yeah, your processor may die, like before you actually replace it. But if it's like 70, 80 degrees at load and like that only happens just occasionally, like maybe a few hours a day or something while you're gaming or something like that, then yeah, I don't think longevity is going to be a problem at all. Yeah, more than likely you'll either replace it or something else will fail before the processor fails due to high temperatures. Though processors are fairly resilient to it. Same thing with GPUs. Like the GPU die itself is usually capable of running at fairly high temps, but that doesn't necessarily mean other components are safe running at those temperatures. Yeah, like John says, the HP DV6. Though the problem with the DV6 series, or actually it was the DV6000s that were recalled, is that the heat would kill them, but it's because NVIDIA spec'd the wrong solder. Yeah, well, it wasn't so much that it was just lead-free solder in general. It's just I think it was like the wrong type of solder. Because they have to use lead-free solder anyway because of environmental requirements. So like it would have been lead-free solder, but I forget what the details were, but they spec the wrong type of solder. And then it caused the solder to degrade over time as it thermal cycled, as it heated up and cooled down, and then it caused the chipset, the NVIDIA chip, to lose contact basically, and it'd fail. So yeah, I mean, heat contributed to it, but the root problem wasn't the heat, it was the solder. So if they had used the proper solder in the beginning, then the chip running hot wouldn't have caused all these failures. But yeah, I mean, there are other components though that don't necessarily tolerate running so hot for long periods of time. Like power supplies would probably be one. Most consumer power supplies usually aren't really rated for running continuously at high temperatures. Let me think what else. VRMs, like whether it's on the video card or the motherboard, if they're not cooled adequately, then yeah, running those for extended periods of time at high temperatures. Oh yeah, I don't know what else to leave it open to. Yeah, that could damage them. SSDs, I don't think there's really enough definitive data on the effect of high operating temperatures on SSD longevity. Because like Google has a famous white paper on a analysis of, I think, hard drive failure rates as it relates to temperature across their data centers. Because I mean, talk about somebody with a large sample size of hard drives, it'd be Google. And I think because the common wisdom has always been that high temps kill hard drives, and I think their paper showed that yeah, like past a certain point, yeah, high temps kill drives if it's just like really hot. But actually, I think their paper showed that counterintuitively, like running the hard drives a little on the warm side, or just, I guess, kind of like normal operating temperature, just kind of like, I don't know, 30, 40 degrees Celsius ambient, like I think more like 40, that they actually like lasted longer than drives that had lots of extra cooling to try to make sure that they would basically run at ambient temperature. So yeah, I think what it was is that the little bit higher temperature, kind of like the oils and stuff for the bearings were just a little bit thinner because of the higher temps, and they actually lasted longer. But yeah, but I think it was like a kind of like a bell curve, like trying to like running the hard drives at like pretty much as close to ambient as possible actually resulted in like less reliability, and then kind of a middle area of like kind of a little bit elevated temps but not super hot resulted in the best reliability. But then like, yeah, after a certain point it kind of drops off again, and just like if really high temps, and then the reliability just falls. And then yeah, like really, really high temps will just like kill anything electronic. So it's just like you just kind of have to moderate it. Oh yeah, I think that's there it is. Let me pull up the chart. Yeah, so here it is. I think that's annualized failure rate. And so yeah, average temperature. So yeah, actually you can see like, yeah, so the temperature actually like from 20 to 25 is actually fairly high. 20 to 25 degrees Celsius. So like trying to cool the hard drives as much as possible actually results in fairly high failure rates. And then you can kind of see from 25 up to about 45, or like it kind of, I guess, is still declining from 25 to 30. And then from about 30, 35 up to 45 or so, it's fairly level. And then past 45, the failure rate starts creeping back up. So yeah, like actually running your hard drive from about 30 to 45 degree Celsius operating temperature actually seems to be the ideal, at least based on Google's data set, which of course is like, it's Google, so like the way they operate drives is very different than consumers. But it's just kind of interesting to note that the idea that like just trying to keep your hard drives at the lowest temperature possible actually may increase the failure rate. So it's just kind of interesting. And I don't think that really is the same with CPUs. I don't think running your CPU as close to ambient's gonna result in like higher failure rate because they're not mechanical devices. But yeah, I mean, I don't think letting it run at like 60, 70 degrees is really that big a deal like some people think it is. Yeah, I mean, yeah, SSDs are kind of a weird thing because they're solid state. So like unlike hard drives, there's no moving parts in that regard, but they are susceptible to heat in that because like the problem with SSDs, and it's not so much of a problem now with the modern 3D NAND stuff, but it is definitely an issue with the 2D planar MLC and TLC. Let's see, because the problem is that the electrons will leak. Anantech has a really good article somewhere about this, but I don't remember which one it is because they have tons and tons of SSD articles. But basically, the problem with SSDs, I don't know if I'll find the diagram I'm thinking of because I don't remember which article it's in. Oh, okay. I think this is kind of, it's a really bad picture, but I think this kind of goes over it. So the problem is like each cell stores electrons, and then that's how it stores like data, like a bit. And so the problem is like over time the electrons leak out of it, and then eventually it gets to the point where there's not enough voltage for the controller to reliably read whether it's like a 1 or a 0. And the problem is like, well, I guess SLC, it's literally like 1 or 0. It's either has like a certain charge or it doesn't. MLC has what, 2 states? So it's either, or no, MLC has 2 states. Yeah, 2. So it's either, let's see, ground level, the first state, or the second state. So there's like 3 states it has to be able to read, 3 different voltage levels. So makes it like a little bit less leeway for error. But then TLC, it goes nuts because it's like 0 state, the first state, or I don't know. I'm not a math person, so it gets a lot more complicated though. Or there's like a lot less differentiation in voltages between the different states. So they're much less, they're much more susceptible to electron leakage as the electrons like leak out of the cells, especially because with planar NAND, in order to increase the density, they kept having to go smaller and smaller and smaller process geometries. So like the cells were smaller and smaller and there were less electrons in there to begin with, and then you compound that with TLC where you're trying to read a bunch of different voltage states, and so yeah, it very much became a problem where like degradation. So like the where this comes into temperature is like running it at higher temperatures. So like higher temperatures, the electrons are able to move about more freely. So then in theory, then they're more susceptible to leaking, which then degrades the longevity. Though that's kind of been reset with 3D NAND, because 3D NAND basically achieves high densities by stacking the NAND on top of each other, like exactly like it sounds like it's 3D. And I think Samsung is currently at 48 layers. So you have like a 48 layer deep stack of NAND. And what it is, they're able to, because they can use the stacking to achieve high densities, is that they're not so reliant on small manufacturing process. So it's actually manufactured on what would be considered a relatively big, like an old process node. But then they stack them up in order to make sure that the SSD isn't like humongous. So that they have like, they can still keep the same amount of storage in a relatively small space, even though they're using like a bigger process. So I don't think it'll be as much of an issue because I think everything looks like it's going to be transitioning to 3D NAND. I don't think there's much of a future for planar NAND, for at least for or like enthusiast SSDs. But yeah, you're right though. The 950 Pro, I'm pretty sure the 950 Pro. No, the 950 Pro actually does use VNAND. I'm thinking of the SM951, which was its predecessor, which had the same high performance controller, but it used planar NAND. So the 950 Pro, I don't think is going to have much problem with longevity because it's using VNAND. So like I said, it's an older process node, so it's going to be less susceptible to heat. So I think where we'll definitely see interesting results in a couple years will be those high performance planar NAND drives. So that would be the mainly the SM951, and I can't remember the SM961, the 960 Pro's predecessor. I can't remember if it uses planar or VNAND, but definitely the SM951 because I used to own one, so I know for sure that it's planar. Yeah, I've done a lot of reading. I mean, I don't really know as much depth as a lot of people that but yeah, it's just, I don't know. Temperature interests me because it's just like, because I don't know, it's just it's so annoying that so many people are so stuck on low temperature. Like it's not necessary. Like it really just is not. Like running at ambient doesn't really get you that much anything over running it at like 40, 50, 60 degrees other than just like more noise because you have to have more cooling. Like you could, in like an ATX system, like you could easily have both. You can have like low temps and low noise, but on SFF that just becomes almost impossible. So you just had to pick one or the other, and I always pick low noise. So yeah, I just get very frustrated that so many people are still stuck on like low temperatures when it's really not necessary. It just isn't. Yep. Yeah, small, quiet, or cool, pick two. But I mean, like I was saying though, with good design, you can kind of get pretty good results on all three though. Yeah. Oh yeah, you could just like move to Alaska or like Norway or something like that and just like stick your computer outside the window and just run the cables inside. Yeah, and then you can have all three for sure. Then you just got to worry about condensation. Oh yeah, bears. Got to worry about them polar bears running off with your computer. That's true. But yeah, like maybe the Dan A4 to a lesser degree, but yeah, definitely like some of these SFF designs where like the various components are right up against like the various vents, so like you can actually achieve some pretty good cooling with these things without having to sacrifice noise too much. Like my only problem with it is like I really don't like having to have such a small CPU heatsink though. I do usually prefer a little bit beefier cooling on the CPU. So I mean the A4 is nice, but I don't think I'll ever get one for myself because I just don't like being stuck with like a 40 millimeter CPU cooler or whatever it is. Yep. So the case that shall not be named will be out eventually. Soon. Yeah, soon TM trademark. All right. Any other questions or anything else you guys want me to talk about? Oh yeah, I guess speaking of small and like noise and then powerful, like I've been testing the FSP, what is it? The FSP-FP 500 PT. It has a weird model name, so I can never remember it. Yeah, the FSP 550 FSPT. I don't know. This thing. So this is the one iFrolict on the forums been trying to kind of like make a thing for a while now. So it's on Amazon now. Is this it? No, this is the 1U. Where's the... Amazon. Huh. It was on Amazon. Where'd it go? Huh, that's weird. Oh, here it is. Okay. I'm not sure why it's not on that other page. Yeah, so I bought one of these. Yeah. So, yeah, it's not quiet at all. At least not at load. So, yeah, because, I mean, that's kind of the thing is like just physics. Like, it's a 40 millimeter fan, so there's only, yeah, so this is fairly common with Flex ATX because Flex ATX is designed for 1U power or 1U chassis, which 1U chassis are 41.5 millimeters tall, I believe. Something like that. And then the power supply is basically that. So in order to fit the fan, because the fan's 40 millimeter, they actually had to make a cutout in the casing because the casing's not, the power supply itself is actually just as tall as the fan. But yeah, that's a 13,000 RPM fan. And it's not even a normal size 40 millimeter. It's only 15 millimeter thick, whereas most 40 millimeter fans are 20 millimeters thick. So yeah, it's pretty loud at load. At idle, it's actually surprisingly quiet. I was actually very, very surprised at how quiet it is at idle. But yeah, at load, the fan is going full speed at load at like 400 to 500 watt load. It actually is going 13,000 RPM. So yeah, with power supplies, it's very much it's either quiet, cool, or small, but you had to pick two. So yeah, I don't know about like as far as airflow goes. Or actually, let me see. We can look at. This is one thing that I really, really, really hate about consumer fans is that there's just like no specs, or at least, or no, there's specs, but they're basically worthless because like they're just not accurate at all. But if I can find it. Okay, now the pictures must be on my... Oh, I think the pictures are still on the card, my SD card. So it's a... Well, we can just look it up. It's a Sanyo Denki, which, Sanyo Denki doesn't really have much recognition for consumers, but they're a really big name in the server world. So basically, they're one of the big server fan companies. So most people are familiar with Delta. So there's Delta. There's actually quite a few. There's Delta, Nidec, Sanyo Denki. Was it EBMST or Pabst? There's a bunch of them, but definitely Sanyo Denki is one of the bigger ones as far as like high quality server fans. And so that's what's in here. So it's a 40 by 15. I think it's a 9GA series because the other one is a... Yeah, I'm pretty sure it's a 9GA series. So what it is they actually have proper graphs. So you'll have like an airflow versus PWM cycle for that, and then like for the voltage ones, you'll have like voltage versus airflow. And like their actual curves, they're because what happens is like you'll get your best numbers if there's like no static pressure. So like the fan is just like kind of in open air, you're going to get the highest airflow measurement. So that's usually consumer fans, that's usually how they're measured. Like you see like a CFM spec on a consumer fan, that's at 0 static pressure. So the problem is that in the real world, your fans are not running at 0 static pressure. Especially a PSU fan or a CPU fan or a GPU fan, is that they're up against a so there's back pressure from the components it's sitting up against, and then there's also like pressure from the vent that's in front of it. So the problem with this FSP unit here is that it is completely crammed. Like the internals of this thing are like, there's almost no air. Like it's amazing like how much like so little free space there is inside of this thing. And then you have a fairly restrictive grill, so there's quite a bit of static pressure on the fan. But that's the nice thing with a proper industrial fan, is there's actual proper graphs. So you can see here like a graph showing you like the airflow, but also airflow plotted against static pressure with various voltages in the case of the voltage controlled ones, and then PWM cycle in the case of the PWM version. So this is amazing. Like you never get these type of data sheets for consumer fans. So you can see, I mean, part of the problem though is I don't know exactly like what static pressure it would equate to. Like on a normal air cooler, like how much static pressure would there be versus like a dense water cooling, like a dense radiator or something like that. I don't really have a good like idea of like where on this chart like certain use cases are, but it's just awesome that these charts are even here, because you just can't get this kind of data normally. But anyway, so yeah, this is the fan that's in it. It's like a variation of this. I think it's this one here. It's the 9GA0412P7, but then it's got like, it's a custom fan. I don't know what the differences are between it and the normal one on the spec sheet, because the one that's in the power supply is a G007, whereas the spec sheet is a G001. So like the last couple numbers, at least Sanyo Denki's convention is that refers to customer specific models. So if they do like a custom version, it'll be like whatever, the last couple numbers will be different. So like it's based off of this, but then there's some some customization of some kind, which possibly it could just be like a certain like FSP wanted a certain length and a certain connector for the cable for the wiring. So that may be all it is, but I don't know. But yeah, it's 13,000 RPM. And yeah, it is very loud at full load. But yeah, surprisingly, it's pretty quiet at idle. But yeah, it's not pushing a whole lot of... Oh yeah, that's what I got into this for. It's not pushing a whole lot of air at idle, because it idles at about... I think it idles at around 1500 RPM, which that may be what they customize, because I think the stock one only goes down to about, it's kind of hard to read it, maybe about 3000. So that would be pretty low on the, okay, I guess the graph doesn't even go that low. But yeah, airflow, so that's 50, and then this would be maybe 10 or 20. So we're talking probably when it's idling, it may only be like 1 or 2 CFM. Like it's pretty low. So not a whole lot of air. But then again, I mean, if it's idling, because it's platinum rated, so I always forget the numbers offhand, so we can calculate it. Oops. So platinum rated at idle. Let's see, that's 90% efficiency at 20% load, which 0.2 times 500, 100 watts. Okay, yeah, because about idle up to about 100 watts or so, I noticed that the fan only runs at about 1500 RPM. But let's say 100 watts, and it's, what is it? 90 watt efficient times, or no, divided 0.9. So it's 11 watt waste heat. So 11 to 12 watt waste heat. So even though the fan at idle is only pushing like 1 or 2 CFM, it's only 11 watt waste heat. Like that's maybe a tad bit too much to dissipate. Well, 11 watt. I mean, because there's definitely like computer parts like CPUs and GPUs that run at 11 watt waste heat idle, or like fanless, I should say, but they usually have like pretty beefy heat sinks. Whereas this thing really doesn't have that much heat sink inside of it because there just isn't space for it. But I mean, 11 watts to dissipate, I mean, that's not much. So yeah, even though at idle the fan's like barely pushing any air, it really, that's fine because there's so little heat. What is annoying though is that, let's see, platinum rated says 89% efficiency at full load. So let's say that's 500 watts divided by 89. So, and then minus 500. Whoops, I can't do this. Minus 500. So that's 62 watts of waste heat at full load. So, I mean, it's still not that much. So it's kind of annoying that it's running at 13,000 RPM to dissipate 60 watts of heat. Yeah, I mean, it is what it is. Like, it's a server power supply, so low noise isn't really a primary concern, because it's designed to go in a server rack somewhere behind a thick door where you can't hear it. So, yeah. So, I don't know. It's a cool unit. At idle, it's not too bad. At low loads, like maybe up to 200 watts, it's not that loud. It's definitely not quiet, but it's not like super obnoxious. But anything above 200 to 300 watts, it gets pretty loud. So, yeah, it's about the same waste heat as an i3. It's a good point. And yeah, that's an interesting thing is like processors, whether it's a CPU or a video card or anything like that, if it's a processor, processors do not do mechanical work. Like they don't. There's not like they're not like a fan where it converts like electricity into like physical motion. So like all the power consumed by a processor gets converted to heat. So like, I mean, I see a lot of misconception where like people talk about like they want to reduce the heat of the CPU, so they're reducing the temperature, but they're not reducing the heat output, because the heat output is the same, even no matter, well, to a degree. So if it's running at like ambient temperature, you just got like a massive heat sink, like a Noxia D15 or a water cooling setup or whatever, and it's running at ambient, it is drawing less heat than if it's running at elevated temperatures, because it's able to run at a little bit lower voltage, so it's a little more efficient, but it's not a huge difference. Overclocking is a whole different matter, but for the most part, it's usually like, to a degree, no matter the temperature, it is running mostly the same heat generated. It's just how good your cooling is how good it is at dissipating the heat. So then the processor runs at a lower temperature, but the actual heat generated is the same, or just about the same. So the only way to reduce the actual heat generated is just to consume less electricity to begin with. So that means like undervolting or just getting a more efficient system. But yeah. Yep. Yeah. So like, yeah, water cooling, because it lowers your temperatures, it means your room will be cooler. That's actually like not true at all. Because it's dissipating the same amount of heat, and that heat's getting dissipated into the room, whether the CPU runs at 20 degrees Celsius or 80 degrees Celsius. So that's true. But yeah, an external loop where it's just like outside the room is really the only way you're gonna get around that. Yeah, so I mean that is, I mean, yeah, because what it is kind of what I was saying with the do I still have the graph open? No, I don't. So yeah, because like airflow, like as static pressure increases, the airflow goes down, but also the turbulence goes up, and so the noise goes up. So a so yeah, like the vent pattern and then the distance between the vent and the fan both have an effect. So like a very very open pattern, like just like a less dense vent pattern will have less of an effect, and then also like the further away it is, the less of an effect it'll have. So a very dense fan pattern really close to the fan is like worst. So that will get you the worst cooling and the highest noise. And the problem with the end case, or I mean the Dan A4 and also the end case, is that they're using Lian Li's standard vent pattern, which is a relatively dense pattern. Well, okay, so what it is like, oh come on, when I want a picture, I can't find it. Okay, what? Well, anyway, so like it I guess it doesn't look that dense, and I guess it's not that dense overall, but the problem is it's a lot of little holes. So there's still quite a bit of material in between the different holes, and so like it's still a fairly dense pattern, I guess, in that regard. So yeah, having like fewer bigger holes, I mean, to a degree, I mean, of course you could go to the other extreme and just have like a couple big holes and then tons of metal between them, which would defeat the purpose. But like, yeah, like a pattern with like fewer but bigger holes would probably be less of an effect on airflow and noise. And then also, like in the Ncase M1, because it's a 3-slot case and there's a little bit of space even beyond the third slot, is that the video card's fans aren't right up against the vents. Whereas on the Dan A4 they are, and like the fans on the video cards are thin fans, because there just isn't room for anything else, and so they don't have a ton of static pressure anyway. And then you put it like literally almost right up against this vent, and then yeah, I can imagine that the noise is a problem. And same thing with the CPU fan, is that the CPU fan is like right up against the vent. So yeah, you just kind of have that same problem, which is actually, and we kind of talked about this on the podcast this morning, is that this is kind of why Nasser is going with this layout for the project sidearm. Is he's purposely gone with this layout to avoid that very problem. So rather than having the fans for like the video card especially up against the vent, and then having to like use those thin fans with the poor static pressure to try to pull through the vent pattern, is that he has the video card flipped around so it's the fans are facing the inside, and then you got like 120 millimeter fans on the bottom of the case providing it air, so the video card fans aren't having to fight against the vent grill that's right up against them. They just kind of are somewhat open air, at least the space between it and the back of the motherboard, and then like it's bringing in air, it's getting fresh air from the fans on the bottom. And then the way his current proposal is laid out is that this this kind of bottom section here serves as basically a big air gap between the fan and the like the bottom of the case. So air can kind of come up through there. It provides it looks like about a 15 to 20 millimeter gap between the bottom of the case and the fan. So that way it's not right up against a vent. So kind of to reduce that turbulence and that effect on airflow. So yeah, he's kind of like taking all that into account with this design. Yeah, so different patterns will have different effects. So like, yeah, having like a bunch of small holes versus say like maybe slots. So even if the densities, even if the I think it's the free air ratio is the technical term, like how much what is the ratio between the amount of free air, aka the holes, versus like the surrounding material. Yeah, even for fairly similar ratios, like the shape and size of the holes can have effect on the noise. Yeah, I mean, the problem is I think the only way to really empirically test it would be if you have a panel with a bunch of different patterns, or like you have a bunch of different panels with different patterns, and then like test it with different fans with different spacings, and then also different types of fans, because like a 25 millimeter fan that's designed for static pressure will have a lot different effect than like the thin fans used on video cards, for instance. So I don't think anybody really knows what the ideal pattern is, because I mean, there's just testing something like that would be rather both time consuming and I think expensive. And then also the thing is like what may be the like ideal fan grill pattern may not be the best one as far as like manufacturing and aesthetics. So you kind of have to consider that as well. Let's see, highest fan speed, low fan speed. So the loudest was the turbine, the slats, and the circles. Yeah, I can see that. And I think, yeah, like the swirl and the loose swirl, I think K888D was testing that with a custom front panel he's experimenting with that has kind of like a swirl pattern. And I think he did find that it does result in quite a bit of improvement in noise. Wire mesh swirl. So, yeah, the slats, though the particular pattern that they have for the slats is a fairly dense pattern, so I could see why it performs so poorly. That doesn't surprise me. And this kind of is like an SFF problem, is that, I mean, having a big air gap between your fans and your panels just doesn't really work if you're trying to make the case small. So there's really like, there's only so much you could do, because I mean, like the Dan A4, I mean, yeah, he could make the case a lot wider so there's a gap between the panel and the video card, but then it's like at that point it's not really much smaller than an Ncase M1, and then you have like it's much more complicated and expensive because of the riser, the 3M extender, so it's like I mean, it's just kind of a trade-off. So at some point it's just like, what are you going to do? If you want it to be so small and so slim, then it's just kind of what you have to do. Is the vent just has to be right there. Like, you think it would look better or look worse with the swirls? I think it would look worse. Yeah, I agree. So that's kind of the thing, is like, there's like A, manufacturability, B is, well, not in any particular order, but yeah, manufacturability, aesthetics, and then performance. Like, you had to balance all three of those when it comes to case design, or vent design, I should say. So in with the Dan A4 and also the Ncase M1, like the particular vent pattern that they're using is more for aesthetics and manufacturability, because they look nice. I mean, there's no denying. Well, I mean, of course, beauty is subjective and all that, but I think it looks nice, and I think most people agree that this vent pattern looks nice. Like, aesthetically, it matches the style of the case. So there's that. Manufacturability is basically because this is like the default pattern that Lee uses. And what it is I think people don't realize, because people have asked about doing different vent patterns for the Ncase, especially, as that's been suggested several times over the years. But what people don't realize is that this vent pattern is made using custom tools that Lee and Lee has. They use it on like many of their cases use this pattern. So they've invested in custom tooling in order to cost effectively produce this. The problem is that if you're somebody like the Encase team or the Don Dan team, or not really team, it's just him, but and you're using Lee and Lee to produce your case, like you're basically limited to what tooling they have unless you're willing to pay them to buy custom tooling to use for your case, and it is expensive. I believe that the tooling that they use for this vent pattern is some kind of I forget the technical term, because like it's punched, but it's not every single one of those holes isn't punched out one at a time, because that would just be insanely time consuming. Like they're punched out in like groups, like they have a multi, I think it's a multi-die punch or something like that. I forget the proper term for it, but they're very expensive because it has all the different holes all had to line up perfectly in order for it to work. And I think Nasser has said that he's asked Lee and Lee about it. Like I think he wanted to use thicker panels, because the panels on the M1 are a little on the thin side at only 1.5 millimeter. And I think he wanted to do like 2 millimeter thick aluminum, but the tooling that Lee and Lee has isn't really suitable for more than 1.5. And he asked about how much would custom tooling is to do the same vent pattern but on thicker aluminum. And I think he said that it would cost as much as a nice sports car, like a Porsche. So I mean, we're talking like tens of thousands of dollars for tooling just for a slightly different, like just for the same vent pattern in slightly thicker metal. Like it's insane. So yeah, so like the Dan A4 and the NK-1, the vent pattern may not be the best as far as a performance standpoint from both airflow and noise, but like manufacturability and aesthetics kind of went out. So it just kind of depends on your priorities. Oh yeah, his windows. Yeah, he posted it in the. I haven't kept up as much. Oh yeah, thanks. I haven't kept up as much with his project lately since it was successfully funded, so it's like that's cool, but it's not something I'm personally interested in. So okay, I guess this is on the CPU side. So this must be with a X99 chip if he's using the Dynatron. But I don't know. This is why I'm not a fan of Windows though, because like I don't know. Like I've yet to see a window that has a vent pattern that looks good in a window. Yeah. And I guess this kind of comes back to like the NK sidearm, is like the reason for its kind of unusual layout is that it can have a window, but since it's relying on airflow from the bottom fans, then it doesn't have to have a vent in the window, because it's hard to do a vented window that looks good. It's just, I don't know. I've yet to see one that I liked. That forum looks dated. Oh, hard forum? Yeah, it's just a styling thing, because they used to use V-Bulletin for the longest time, which I hated, because V-Bulletin... Okay, well, V-Bulletin at the time was a really good forum. Like, it gets a lot of hate now, but it's important to remember that when it first came out... oh yeah, that is pretty bent. Yeah, when it first came out, it was a good system, like V-Bulletin 3. But the problem is that V-Bulletin 4 was basically a disaster, and so a lot of forums stuck on V-Bulletin 3 for like ever. And like V-Bulletin 3 came out in like 2006 or something like that. It's ancient. So hard form is actually running Zenforo now, which is the same one that we run on SFF Forum. So, I mean, if it looks outdated, then it's just the theme. I mean, the actual forum software itself is the same one we use. Yeah, this one's definitely got quite a bend to it. I think this is some Scythe. I forget which heatsink this is, but yeah, it's a bit too much mounting pressure. Though, like a little bit of a bend in the motherboard's actually normal. Like they're designed to be able to handle that, but that seems a little bit beyond spec. Yep. Oh yeah, looks like he's experimented with different vent patterns. No, I mean, like to me, like all of these just like look weird in a window. So, yeah, because I think he's experimented with making the window just. I think somebody mentioned putting the window on standoffs, so there's like a gap. So, to me, I think it may not be the best performance, but I think that would be the most logical design just for aesthetics. All right, but any other questions or comments? Oh yes. So we did not get any pictures of it of the cooling, because when Drew, I think what happened was Drew was at the Ace Rock booth, and I think he didn't have a chance to take apart the system there, so we didn't get a good look at the insides. Let's see. But there was somebody else who got good pictures of it. Ah, here it is. Let's see. Yeah, here. So the let me zoom in. So the CPU cooling is basically your standard cooling. So stock heatsink or something equivalent. So nothing unusual there. But the MXM cooler is it. I originally thought it would be something like a blower type cooler, like you would see on a laptop, but it's actually more. It's fairly straightforward, like heatsink. So what it is like it's kind of hard to tell from the picture, but it does look like you have like several heat pipes and then heat sink just sitting on top of the MXM card, and then you just got like it looks like a slim 80mm fan sitting on top of it. So it's a fairly straightforward design. Yeah, really nothing too special. And what it is that the bare bones kits, at least, I'm not sure, because like I'm not sure how it's going to work if you buy the motherboard by itself or if it's even available by itself. And maybe they just have the web page for it, but you can't actually buy it standalone. But the barebone kit will come with the AC adapter, the case, the motherboard, the MXM card, and then the cooler for the MXM card. So it will come with this heatsink. And then the mounting holes on MXM are fairly standardized, I believe. So yeah, it should be well, if it follows the standard, which not all MXM cards do, but if it follows the full MXM standard, then the mounting holes should be standardized. So then, yeah, you should, in theory, be able to take this MXM heatsink and then use it if you replace the upgraded or whatever. So, yeah, that's the cooling. I've been toying with the idea of designing like a water block, like a mono block So it would cover the CPU and the MXM card, but I don't know. Like the problem is like it's not something I would actually want to use for myself because like I just can't stand pump noise. So it'd be more like I would do it just for the challenge, but it's not really something I would personally have much use of. So I don't know if I'll ever do it. I don't know, because the problem is like it. It's a cool product, and I'm glad it exists because it's pushing the boundaries. But I don't know, it's not really something I would personally use. So I don't know if I'd ever design anything for it. But it's cool to think about, and I'm sure somebody will do it anyway. Because yeah, you're right. I'm sure. Because I mean, that's the thing is that like like your traditional layout, computer layout with your like video card perpendicular to the motherboard, and not only that, but the heatsink is on the wrong side of it. It's like on the other side from the CPU. So you can't really have any kind of shared cooling system. But here, yeah, because the video card is not only in the same horizontal plane as the motherboard, it's also the chip is on the same side of it as the CPU. So that makes a monoblock very feasible. So yeah, I'm sure I wouldn't at all be surprised if people make custom monoblocks, and I don't know if it's a popular enough product, we may even see like aftermarket blocks from like EK or Bits Power or somebody like that who like somebody who makes monoblocks for other motherboards. So the thing with like because MXM is standardized, so like I said, the heatsink if the MXM card follows the standard, then the heatsink is interchangeable. So then, yeah, in theory, a monoblock should also be interchangeable. Um, yeah, so wouldn't it to be less desirable to use a monoblock with something connected? I mean, I don't see why it'd be any more or less desirable because I mean, you're not going to be swapping up CPU or the MXM card very often. So, um, yeah, so this like there's different versions of MXM, and I think this is what's called Type B, if I recall. I'm not sure what all the differences are. I haven't looked that closely at it, but yeah, it's like thin ITX in that the card is standard, like the size of the card is standard, the holes to attach it to the chassis is standard, and then also the position and mounting holes for the GPU itself, like the actual chip, is standard. Um, so yeah, it's all standardized. So yeah, in theory, yeah, the cooling if and the problem is like not all MXM cards actually follow the standard because a lot of them they're of the MXM like connector and form factor, but like they're only really intended to be used in like a specific laptop, so they don't really bother making it fully to the standard because it's not ever going to be interchanged with anything else. But yeah, MXM cards that actually follow the standard, then yeah, they are interchangeable. Um, but that's kind of the thing though, is like they don't. It's kind of like that's the problem with standards is that like not everybody necessarily always follows them all the way like to the letter. So you have to kind of be aware of those outliers. Um, but yeah, so yeah, in theory though, yes, the like a monoblock wouldn't only be good for that specific combination of like that board and then like a certain MXM card. In theory, it should be interchangeable with any MXM card. Um, so yeah, so it actually, if anything, a monoblock on this would actually be more viable than like a traditional system where like you may have like a block on the motherboard and then a block on the card, but like a full board, like a full coverage block on a video card is really only good for that particular card. Because video cards, like the connector is standard, like PCI Express connector, and then like the rear bracket, and there's a couple other things, but like everything in between is basically like custom. So like there are custom or like there are universal water blocks for video cards, but they basically have to like the block itself is universal, but then you have to have like a custom mounting solution. So there's not really any such thing as a universal full coverage block for a video card because you just can't. I wouldn't be surprised. Because really, it only makes sense to offer upgrades if people actually want to use them to upgrade. And I imagine like an all-in-one that probably not very many people ever upgraded it. But this is going to be sold as a barebone kit. So like by definition, people are going to be assembling these things. So you would think that at some point people would want to also upgrade it. So, I mean, really that's just the thing is like the availability of the cards is going to make or break micro STX. So like if AceRock can make them printable and affordable, then I think it'll stick around for a while. But if they fail to do so, I think micro STX is dead. Because like, yeah, I mean, if you can't buy it and then upgrade it, then it's kind of pointless. No. Any other questions? Yeah, I don't know what's up with that. That it really annoys me that like nobody talked about it. Let's see. There's the non-tech article, our article. Okay, there's a couple now. So Tech Power Up, Kit Guru. Though I think several of these just used our. Oh no, Tech Power Up has their own pictures. Kit Guru just uses the press photo. And oh, these Overclock 3D is just using the Tech Power Up pictures. Yeah, that's basically it. Yeah, and then the non-tech used our pictures, which is funny. And yeah, that's basically it. There's like was practically no coverage of it, so that was disappointing. But I don't know. Yeah, probably. Cause yeah, I think let's see. I started at 3, and we're coming up on 6 o'clock. So yeah, we're about 3 hours in. So yeah, I guess if there's not any other pressing questions, yeah, we can just call it good. So yeah, last call for questions. Anybody? Oh, me? I'm James. So yeah, there's the 3 J's. So John is, yeah, Confucius is John, and then Playful Phoenix is Joshua, and then Ibophobia, which is me, is James. So the 3 J's. All right. So yeah, if anybody SFF network socks. No, I don't think so. Though that is an interesting idea. Fangirl probably not, because like the cube doesn't really make for that well of a vent pattern, so probably not. But yeah, definitely shirts, and I think we have a couple other things planned. But yeah, definitely shirts though. So I believe I think the current plan is to do shirts, yeah, soon. I'm not sure when. It just kind of depends on how busy Joshua is, because he's in charge of that. So it just depends on when he can get to him. But it should be within the next couple weeks, for sure. So yeah, look forward to that. But okay, well, I guess we'll just stop here then. So all right, so yeah, this is James from smallformfactor.net, and so we'll just call that an end to this. And what it is, oh, I guess I should touch on it real quick. I think I'm about done with the chassis design. I don't think there's really anything left to do. So, like I said, there's a couple little details I need to fix, and then I need to fix the vent pattern, but I'll just do that on my own time because it'd be incredibly boring to watch me fiddle with the vent pattern. Just getting the spacing lined up correctly. So I'll do that. So I don't think this may actually be the last episode for the GPU design, the eGPU case design. So, because I can't think of anything else left to do that would be interesting to watch me do. So yeah, I think at this point this will probably be the last episode, at least of the design part. I may touch a little bit at some point on the process of like exporting it and then getting it ready for like production and stuff like that. But I don't know if that's really worth making a video of. That may just be like a forum post or something like that. So yeah, I think at this point the 18th next week, I will probably do a stream. I don't know what it would be of though. It may just be general sheet metal stuff, or I may just hang out and take questions again. But yeah, so I'm pretty sure there will be a stream next week. But yeah, I don't think it'll be for the eGPU. I'm hoping to be completely done with the design, and then production I'm going to have to kind of figure out because there's a couple things I need to kind of get in order as far as getting it actually like a prototype produced. So we'll see on that. But yeah, I think we'll tentatively plan for another stream next week. So, okay. But yeah, it's been 3 hours now, so we'll just call it quits for today though. So yeah, thanks to everybody for joining and watching and asking me questions. It's been fun. And yeah, so it's James and signing off.